So this video is going to go over classifying functions because we're going to start putting together every type of graph that we have done all year long. And it's important to be able to look at an equation or at a graph and be able to identify what type it might be. So this is just going to be an overview of each of them so you have a nice reference spot to go to. First thing we're going to talk about is stuff that you learned either in Algebra 1 or in the first section of Algebra 2. Okay, the first one here is a constant function, and that means you just have some y equals a number, or really f of x is how we wrote it in Algebra 2. These in a graph are always just horizontal lines. Okay, so for example, maybe you graphed y equals -2, and this red line would be that. That is a constant function. For the next one, for linear, this is when it's of the form y equals mx plus b, which is again an Algebra 1 topic. Again, it could be f of x instead of y. Remember, that's always the same, but in Algebra 1, you typically wrote y instead of f of x. These are just any lines in general, typically. So if I draw an example, this would be a linear function. It has a constant rate of change, whether up or down. You have your y-intercept, all of those primary characteristics. This one looks like it might be y equals x plus 2, something like that. This last one, absolute value, is one we talked about this year in Algebra 2 during Unit 1. You did touch on it some in Algebra 1 also, but we did talk about it quite a bit this year. Your parent function for this looked like this, where you had f of x equals a times the absolute value of x minus h plus k. This is the first time we really experimented with those a, h, and k values that you have now seen in every single chapter of the year. And these are always your V-shaped graphs. So for example, if I sketch one out, maybe it looked approximately like this. Just making up what equation this might be. Looks like my a value is about 1, so I'll leave that as a 1. It went to the right, say 4, so it's x minus 4. And then it went down, call it 2, so minus 2. Again, that's really just made up, but that would have been what that equation may have looked like. Then in Unit 2, we talked about radical functions. So everything that I talk about here, again, really comes from Unit 2. If you're looking back in your notes. In our radical functions, we specifically graphed 2 of them. We graphed square roots, which is when you had f of x equals the square, a times the square root of x minus h plus k, or cube root when you had f of x equals a times the cube root of x minus h plus k. And when we did these, they looked fairly similar. The main difference was that in square roots you had a starting point because we cannot graph negatives under our square roots. It gives us i's. So in our Euclidean graph, your normal xy axis that you're used to, we can't graph that. And in your cube roots, you had a turning point really instead in the middle of your graph, but it did go both ways because you can cube root positives and negatives. Just to give you an example, again, of each of them, your square root functions started somewhere and then went forever to the right for everything we did. Maybe this one. This went left, say 3, so x plus 3. Remember that h value always switches. And it went up maybe 1, so that would be an equation for that graph. For ones with a turning point for your cube root function, it looked something like that, where it kind of flattens off both to the left and the right, but in the middle it gets pretty steep and curves upwards. This one, if I were to write an equation for it again, maybe it's the cube root. This one looks like it went right because these were typically centered right here. So maybe it went right 2 and it didn't go up or down. So maybe that's what your equation could look like. Again, here, the thing I primarily want you to know what the equation approximately looks like, what the graph approximately looks like. Then, Unit 3, Let me move that over so you can see it. We started talking about polynomials in general. So this was both Unit 3A and 3B. Polynomials in general are just when you have something that looks like this. You could have ax to the whatever power, it could be an n, and it's going all the way down to just some constant value. So that n value, again, that could be an x to the fifth, and then you have an x to the fourth, and then a cubed, and then a squared, and then a first, and whatever it is. So you have really your x values all raised to some power throughout. A quadratic is when you have a highest exponent of 2. A cubic is when you have a highest exponent of 3. A quartic is specifically a highest exponent of 4. We didn't really go any higher than that, but technically we could have. When you're dealing with your quadratics, I'll go through these again with your equations. Again, you have a highest exponent of 2, so primarily this looks like ax squared plus bx plus c. We also wrote it in vertex form with that a, h, and k floating around. So that equation can be given to you either way. Cubics, primarily we wrote them as maybe ax cubed plus bx squared plus cx plus d. We didn't really write it any different way in here. You could technically write it something looking like a vertex form, but that's not going to be the priority here. I'm going to give you things that look like this. And a quartic, again over here, really just means you have an highest exponent of 4, so you have ax to the fourth plus bx cubed plus cx squared plus dx plus e. So again, with really the priority here is what is your highest exponent? When we did these, we talked about a lot of little details here, specifically talking about your number of x-intercepts and your number of turns. And so I'm going to briefly talk about that some more, and don't worry, we will go over all of this in detail in future videos. For your quadratics, you have a highest exponent of 2, which means at most you have 2 x-intercepts somewhere here. Okay, for a cubic, highest exponent of 3 tells you have at most 3 x-intercepts. Quartic tells you have at most 4 x-intercepts. We also talked about end behavior, if you think way back to that. A quadratic and a quartic are both even, so their end behavior, it either both goes up or both ends go down. For a cubic, it's odd, so one would go up and one would go down. And so I'm just going to roughly sketch, these functions. A quadratic are most common, so it looks just like a parabola. For a cubic, it could look a couple different ways. It might just kind of curve in the middle. It also might have, bigger turns. They might all hit the x-axis, they might not. So there's 3 different examples of really what it could look like. And your quartic were the ones that looked like W's. Maybe like that. It could, kind of like a cubic, also just flatten out in some places. So maybe, and I have a bump there. Sorry, I accidentally have an extra bump. Ignore that bump. Your bumps can be in different places. Here, I'm not going to write you equations for them because they get much more complicated. What I want you to focus on is specifically what I went over, the number of x-intercepts and the end behavior, because that's really what the priority is going to be as we go through this. You're just going to have to today visually look at a graph and be able to recognize that it might be one of these and tell me which one it probably is. Then in Unit 4, we talked specifically about rational functions, and I gave you the equations 2 different ways. Your equations sometimes had those a, h, and k, and at other times was just 2 polynomials on top of each other, so some p of x over q of x. So for example, to make that make a little bit more sense, you might have x squared plus 2x plus 1 over x plus 1. That would be the second form, where you have just 2 polynomials with variables to a power written on top of each other. These ones did get a little bit more complicated, and so again, there will be a video going over the details. Today I'm just worried about figuring out that shape. With both of these, we had vertical asymptotes and horizontal asymptotes. And then your graph showed up in two of those sections. So maybe like this and like this. It could also show up in the other ones, so sometimes they were like here and here, but it shows up in two of them for the ones we did in this course. Again, writing these equations is a little more difficult, so I'm not going to approximate one here because it could look different from here to here. But again, right now, what I want you to focus on, rational functions, look something like these. You have the two distinct sections of your graph. They're both approaching some asymptotes and things like that. Because as we move forward, it's going to be important that you can identify if your equation looks like this, your graph should look like this, and vice versa. The last two things we graphed were from Unit 5. Trying to move these down for you so I can write that above it. Where we did exponential and logarithmic equations. Your exponential equations, our parent function looked like this, where you had a variable in your exponent. And in our logarithmic equations, it was similar, but now we had a log, and your variable was inside your log. When we did these, both of these had asymptotes, but they had different ones, and part of what we discussed in class was keeping that straight. So maybe this asymptote's here. Our exponentials had a horizontal asymptote, whereas our logs had a vertical asymptote. And your exponentials could go one of two ways. They could be a growth function, go up to the right. They could be a decay function, go down to the right. But no matter what, they approached that asymptote in one of the directions, and in the other direction they went up, exponentially increasing over time. For your logs, what we talked about is for the ones we did in Algebra 2, you are not going to have a graph over here because we can't have a negative value for this whole thing inside of our log. So our graph only shows up on the right side. And again, it either grew or decayed. It might go down like this, or it might go up. But it does approach that asymptote in one spot and then go up or down forever in the other direction. So again, this has just been an overview of really what each of them look like, but I want your priority to be, again, is identifying based on the equation, what does the graph look like, and really what we call that here in class.